inspiration comes from Lie algebras, in particular SL2, and I want to start by illustrating this with SL2. So remember, for SL2, so we're going to fix the generalized Weyl algebra throughout this lesson. But let's look at the example of SL2, which is a case of a generalized Weyl algebra, where the ring R is this polynomial ring in two variables. One of them is H, the H which was acting semi-simply in our irreducible modules that we found before. And this element T, which is Fe. I could have also chosen the Casimir element as a generator, but I'm going to choose T. And the motivation is the following. If I have a non-zero finite dimensional module for this, so for SL2, okay, which is the same thing as a module for the enveloping algebra of SL2, then necessarily, since these two, I mean, if I'm assuming the field to be algebraically closed, which, you know, if I don't say anything, I will be assuming that, then, I mean, I have these two operators, H and T, on this finite dimensional space, and since the field is algebraically closed, they will have a common eigenvector. So there will be a non-zero vector in V, which will be simultaneously an eigenvector for H and an eigenvector for T. Okay, this is always the case. Okay, because H and T commute, I can always guarantee that. You can prove that easily. And so the space of common eigenvectors, which I'm calling V lambda mu, so the space of vectors on which H acts as lambda and T acts as mu will be non-zero. This is guaranteed for any finite dimensional module over an algebraically closed field. And this is just because of the existence of eigenvalues, nothing else, okay? So an alternative way of saying this is, instead of looking specifically at the element H and the element T, I can kind of start going towards a little bit more a more abstract setting, if I want to kind of generalize this picture for generalized Weyl algebras, and think of the ideal of this polynomial ring generated by the elements H minus lambda and T minus mu. Okay, and saying that H acts as lambda and T acts as mu on the space is the same thing as saying that M, all the elements in this two-sided ideal, will act as zero on the space, because H minus lambda will act as zero, T minus mu will act as zero, and any combination and any element in this ideal, which will be this element times a polynomial plus this element times a polynomial, will necessarily then also kill a common eigenvector. So another way of formulating this, which is a little bit more abstract, and that'll be convenient, is to look at this common eigenspace as the set of vectors in V, which are killed by this specific maximal ideal of this polynomial ring in two variables, okay? Which is a maximal ideal of R. Okay, and also, I mean, if we play the same game before when we were looking at SL2, we started just with eigenvectors for H, because as we know, the element T doesn't exist in the Lie algebra. It exists in the enveloping algebra because it's the product of E and F, of the action of well, literally F and E, okay? But we can do try the same game and see, well, if I have this eigenspace here, which now I'm going to think of as this, and E acts on it, does it get mapped into another eigenspace? And the same calculation we did shows you that it does. It goes into a different eigenspace where you add 2 to lambda, and you subtract lambda plus 2 to mu, okay? So if you consider this kind of action, this is kind of, well, this gives you kind of an equivalence relation or a discrete dynamical system or whatever you want to call it. And so it follows that if I look at I mean, even if I didn't know what my module looked like, just assuming that it's finite dimensional over an algebraically closed field, I can conclude that if I consider all common eigenspaces of this form, this will certainly form a non-zero submodule. Because when I act by E, when I act by F, I'm just changing these eigenvalues. So I'm still landing in one of these generalized eigenspaces, okay? So if I started with a simple module, it would have to be actually equal to this. And in fact, I could say a little bit more. I mean, the lambda and the mu should not be completely arbitrary, because with E and F, I can only do certain kinds of things, okay? So this is another way of thinking about representations of SL2 in terms of these spaces which are annihilated by a maximal ideal of R, and this is precisely how we're going to define a weight module for a generalized Weyl algebra. So let me establish some notation. So as you've seen, we're going to be interested in maximal ideals of R. I think I've motivated this with SL2. I'll give you another hint later as why this is reasonable. And by the way, I don't know if I wrote this anywhere in the slides, but for this talk, I definitely will need R to be commutative. Okay, I could have some generalizations with R not commutative, but I mean, all the examples that I've given you so far are with R commutative. The significant examples that are known are with R commutative. I will be assuming this. This will actually be important. So I could relax this hypothesis, but then things would be a little bit more complicated. So we've seen that we're interested in maximal ideals of R. So the space of maximal ideals of R, I'm going to call it max R. Okay. Well, I mean, this will come up. The quotient of R by the maximal ideal M, I will call it Km, just to remind you that this is a field. This is one instance where I'm using the fact that R is commutative, because, I mean, this is the same thing as saying that R modulo a maximal ideal will be a field. So it's a field extension of the field F. Okay, I mean, in a lot of cases, it will be identical. It will be isomorphic to F. For example, if F is algebraically closed and R is finitely generated, then this will always be an algebraic extension of F. And so, if F is algebraically closed, this will be isomorphic to F. Okay, but I mean, it's no. If you, I mean, I'm saying this only if this confuses you. Think of this as F. But I mean, if I change the ideal into another ideal where I act by sigma, another maximal ideal, I will get technically two different fields, although they're isomorphic. But it's important to remember, I mean, they're isomorphic, but they're not equal. And this, again, will play a role. Okay, so I will say that a module for a generalized Weyl algebra is a weight module if it can be decomposed in this way as a direct sum of certain subspaces Vm, one for each maximal ideal of R. And what is this Vm is precisely, as we saw in the example, the space of vectors which are killed by the maximal ideal M. Okay, so in the case of SL2, this was just this space V lambda mu, because a maximal ideal of the polynomial ring in two variables, if it was algebraically closed, looked like what I showed you in the previous slide. Okay, so this I'm going to call a weight space or an eigenspace for M or something like this. Most likely I'll call it a weight space. This is traditional nomenclature. And so the definition of a weight module is simply a module which can be decomposed as a direct sum of its weight spaces. Okay, so for which this is not the same thing as saying that something is diagonalizable, because now we're in a more abstract setting, but you know, that's kind of the philosophy. Okay. So if I look at a certain weight space, and this is not a zero weight space, so it's possible in general, this will be true, that some of these VMs might be zero. Okay, so if a certain VM is not zero, I will say that the maximal ideal M is a weight of V. Okay, and I'll say that the support of the module is the set of maximal ideals, which are weights. Okay, so that's the support of the module, of the weight module. Okay, it's the maximal ideals which actually intervene in the module. So this is the definition. And now we can, quickly do the same computation we did many times. First with SL2 with an H, in the previous slide with these simultaneous eigenspaces. And I can do the same thing here. So if I have a certain weight space, and I act on it by the element x in the generalized Weyl algebra, question is, do I still land in a weight space? And the answer is yes. And I end up in a weight space related to the maximal ideal sigma inverse of M. Okay, so it sends the weight M to the weight sigma inverse of M. Okay, and similarly, Y will shift the weights by applying sigma. Okay, so one way of thinking about this is that x shifts the weights by applying sigma inverse, and y shifts the weights by applying sigma. The calculation, you can do it. It's the same as the calculation we've done before. I'm not going to repeat it. And of course, R acts stabilizing this space. And this is really an equality just because 1 is an element of R. So good, so we know, so we know that if we have a weight module, all of these nice things, I have this nice decomposition, and I know more or less what X and Y are doing, although this doesn't tell me specifically what they're doing, but at least I know where things are landing. Okay, so I get kind of a schematic idea of what this looks like. Okay, so if you don't care or don't know, or it doesn't matter about categories, it's just language. I'm not going to use anything essential about categories, so forget about the word category if you don't like it. But if you consider this the set of all weight modules, okay? Well, if I say it like this, it's not really a set, so I don't know if there are any logicians in the audience, but that's why I prefer to say category. But if I consider this, let's allow this the set of all weight modules, and I'm going to call the set, which is not really a set, as W of A. Okay, and if I'm just interested in weight modules that have support in a specific set of maximal ideals, then I will put that set of maximal ideals here as an index. Okay, so this means weight modules whose support is contained in O. Okay, and as we've seen, the action of X and Y imply that I need to apply sigma and sigma inverse to these maximal ideals, which means that the group generated by the automorphism sigma, remember sigma was one of the ingredients in the definition of a generalized Weyl algebra, it's an automorphism of R. So I need to look at the subgroup generated by sigma. There are not many possibilities. Either this is an infinite cyclic group isomorphic to the integers, or it's a finite cyclic group isomorphic to z mod n for some n. Okay, if sigma has finite order. In any case, let me look at this group, and this group naturally acts on the set of maximal ideals because since it's an automorphism, you'll send a maximal ideal to another maximal ideal. Okay, and I will be interested in the set of orbits. So by this, I mean the set of orbits of maximal ideals under the action of sigma. Okay, so a typical orbit is you take any maximal ideal, you act on it by all possible powers of sigma, and that's one orbit. Okay, I'm calling the orbit space omega, and an orbit, which is a set of maximal ideals, which are all related by sigma, I will call that omega here. Okay, so our first result is that if I have a weight module, I can write it as a direct sum of certain things. And let me explain these things and what they are. For each orbit, so now omega is not a maximal ideal, is a set of maximal ideals. It's an orbit of maximal ideals. So for each orbit, I have a direct summand, which I'm calling V omega, and this V omega is really a submodule. Remember that Vm, when n is a maximal ideal, is not a submodule because X, for example, sends Vm not to Vm, it sends it to V sigma inverse. Okay, so Vm, where m is a maximal ideal, is not a submodule, but V omega, and I'll tell you what it is, V omega will be an A submodule. Okay, what is V omega is the sum of all of the weight spaces associated to the weights in the orbit omega. So m will, these m's appearing here are all of the form sigma to the I of some fixed maximal ideal. Okay, so this is clearly a submodule because when I act by sigma, when I act by x and y, I'm just shifting the orbit, but I don't leave the orbit space. Okay, I'm in the same orbit. So this is a submodule, and it's a direct summand. And so this tells me that any module will be a direct sum of weight modules which have a support in a certain orbit. Okay, so if I'm only interested in simple or even indecomposable modules, I can focus on any specific orbit. I need only focus on a specific orbit because in general, a module will be a direct sum of modules from other orbits. Okay, so I can always assume, this tells me that I can always assume that the support of my weight module is contained in a certain specific orbit. Okay. I mean, this is the same as saying that the category of weight modules is the direct product of the categories of these weight modules where O is an orbit. Okay, that's all we're saying. So I mean, if this confuses you, don't worry too much. Just think that we're going to focus on weight modules whose support is in a certain orbit. Okay, and that we lose nothing by doing so. Okay, you can think about this later if you want. Okay, so the first structural result about weight modules is the fact that this category is stable under sub-objects. So if I have a submodule of a weight module, this will still be a weight module. I strongly advise you to try to prove this. It's interesting. It's kind of an abstract generalization of the fact that eigenvectors with different eigenvalues are linearly independent. So I really urge you to prove this. So submodule of a weight module is still a weight module, and this part is easy now once you prove the first part. A quotient of a weight module by a submodule is still a weight module. So submodules and quotients of weight modules are still weight modules. Okay, I'm not going to prove it. I think it's more fun if you try to do it. And now I'm going to introduce dichotomy. Okay, and I should have checked if this is how you spell dichotomy in English. I didn't, so somebody who's bored with a lecture can check that, and then let me know. Okay, so I'm going to introduce a dichotomy. There are two kinds of orbits. There's some which are linear and some which are cyclic. And what this means is a linear orbit is an orbit that has a maximal ideal, M, here, such that when I act by sigma, I will always get a different ideal. Okay, so all of the, as I run through K, sigma K of M is always a different ideal. Okay, so there's, so for example, sigma squared of M is not equal to M. Okay, this is a linear orbit. Okay, which means that it's just could be identified with the integers. Okay. Or if you want an easy way of saying what the linear orbit is, it's just an infinite orbit. Okay, and a cyclic orbit is one which is not linear, which means that it's just a finite orbit. It's an orbit on which, sigma to the k of m is going to be equal to m for some non-zero k. Okay, and I mean, with the same automorphism, you can have simultaneously linear and cyclic orders. So there's an example here. So if you just take polynomials in one variable, and if this is your automorphism, just sending x to q times x, okay, where I'm assuming q to not be a root of unity, okay, then if I consider the maximal ideal generated by x, then of course when I act by sigma, I'm changing x into q times x, but q is a scalar, it's a non-zero scalar, so it's the same ideal. So this ideal, when I act by sigma, will stay invariant. So this is a cyclic orbit, an example of a cyclic orbit of order 1. But if I consider the ideal x minus 1, then when I act by sigma, for example, I will have the ideal generated by qx minus 1, which I could write as, if I multiply everything by q inverse, x minus q inverse. And since q is not a root of unity, q inverse is not equal to 1. So this is not the same as the ideal x minus 1. And I can keep acting and acting and acting by sigma, and the fact that q is not a root of unity will say that all of these ideals are different. And so this orbit here will be linear. So fixing an automorphism, I can simultaneously have certain orbits which are linear and certain orbits which are cyclic, okay, depending on your automorphism, okay? So this is the dichotomy because the representation theory will really divide here. It'll be radically different in both cases. I will mostly focus on the linear case, which is the easiest one. Okay, I have some things here about cyclic orbits, but I might even skip it because I have too much to cover today. So let's start looking at linear orbits. So imagine you have a weight module whose support is in this orbit omega, orbit of maximal ideals, and I'm assuming that this is a linear orbit. Okay, so all of these, I mean, when I act by sigma, I'm always getting different stuff. Okay, so first of all, my first claim is that under this hypothesis, I'm missing. Oh no, I'm not missing a hypothesis. If I also assume that this weight module is simple, this will force any non-zero weight space to be a simple module over R. And you can think a little bit about this. I mean, if Vm as an R module were not, Vm can be zero, and that's fine. But if Vm is not zero, it should be simple as an R module. And you can, I mean, it's more fun if you try to convince yourselves of why this is true and why I need to be assuming that the orbit is linear to say something like this. Okay, but if I'm interested in simple modules, then these weight spaces need to be simple as R modules. But R is a commutative ring, so the R modules are just of the form R mod M, where M is a maximal ideal. That's what the simple modules for a commutative ring look like. Okay, so the weight spaces will actually look like R mod M, where M is a maximal ideal, and this is a field. Okay, so kind of each weight space will be a field. So the elements there, the non-zero elements there, are invertible modulo M, are elements of R which are invertible modulo M. Okay, so this tells me that the weight spaces should be fairly small. Okay. Now, if I assume, I mean, let's go into kind of a more general scenario because perhaps you're also interested in the indecomposable modules, and this theory also works for that, although I will focus on simple modules. Okay, so assume that I have a module which is generated by some element. It might not be simple, but I can assume that it's generated by a certain element which is in this weight space here. Okay, well, if it's generated by V, then I can get every element in the module just by acting by R and X and Y. And by doing this, I will never leave the orbit of M, as we've already argued. So this module is necessarily in this omega orbit, which I'm assuming to be linear. Okay. And this map here that sends an element of the generalized Weyl algebra A to A times this specific element here in the module V, well, clearly this is a homomorphism of modules, and it's a surjective homomorphism because I'm assuming that the module V is generated by small v. Okay? So this means that the module V is a homomorphic image of A seen as a left A module, which is usually called, I think Alfie talked about this, is usually called a regular left A module. Okay, seeing a ring as a module of itself. Okay, well, but this surjective homomorphism in general will have a kernel. In this case, we know of certain things which are in the kernel. One thing I know is in the kernel is the maximal ideal of R, M, because M is supposed to kill V. So if M is in the kernel, the left ideal of A generated by M, which is this AM here, must be in the kernel. Okay. So what I've just argued is that if I have any module which is generated by a weight vector, whether or not that module is simple, it doesn't matter at this point. If I have any module which is generated by a weight vector, then it's necessarily a quotient of this module here. Okay, and this module here is so important, I'll describe it in more detail. It's so important that I'm giving it a name and I'm calling it A of M. Okay, so A of M is just the ring A seen as a left A module, quotiented by this submodule, which is the ideal of A generated by M. Okay, so we've just seen that if we're interested in modules which are generated by some weight vector, then there will have to be a quotient of this. Okay, in the linear orbit case. Okay, in particular, if you're looking for, I mean, if you again in the case of finite dimensional modules, we know that we know that they will always be of this kind. They will always have some weight. Okay, so this is nice. Okay, so if I further assume that V is simple, okay, and this is mostly what I'll be interested in, then V we already know that it's a quotient of the module A mod M, but if V is supposed to be simple, then it must be a quotient of A mod M by some maximal submodule N. Okay, and now we're going to see the representation theory revealing itself, how nice this works. So first, let's study this this is kind of a universal module in a certain sense. This tells me that any module which is generated by a weight vector of weight m must be a quotient of this module. So it's universal in that sense. It's a nice object. So first of all, I can describe it like this. Okay, so remember, these are those fields, which in a lot of cases will be just the field F. So the module looks like this. So there's kind of these sort of basis elements, and I have these fields here. Okay, I have a countable kind of basis. Okay, this is always true. And a surprising fact for someone who's never seen Lie theory, and a not surprising fact for somebody who's seen Lie theory, is that this module has a unique maximal submodule. Okay, so this n that I had here, which I said it was some maximal submodule, in fact, it's not some maximal submodule. It's the only maximal submodule that A of M has. Okay, so this kind of universal object has a unique maximal submodule. And for those of you experienced in Lie theory, do not jump to conclusions. This is not a Verma module. Okay, if you know what that is, it's not a Verma module. It's close, but it's not. Okay, so this is a very nice property, and so this tells me that any simple module that has m as a weight must be the unique quotient of this universal module by its unique maximal submodule. So it's essentially canonically described. So before I move on to give you an idea of how this is proved, let me just capitalize on this. This means that if I'm interested in simple weight modules, in the case of linear orbits, I have this object, which is here, which is not too complicated to describe. And this has a unique maximal submodule. So my goal in classifying, in finding the simple modules in this category is just to find this maximal submodule, to determine what this maximal submodule looks like. Okay? Given m in a linear orbit, I just need to find what is the maximal submodule n of m. Okay, so it doesn't seem too complicated. Of course, when you go to practice, things can sometimes be more complicated than in theory, but in theory, at least it's simple. Okay, so how do you prove this? I mean, there are more details in the slides, but I think I prefer to give you the important idea that will help you get there and understand what's going on here. So we've seen that the generalized Weyl algebra has a nice basis with respect to R, given by the powers of x, the powers of y, and I've isolated here the element 1, which I could have inserted here to make it more conspicuous. So if I can look at the ring A as a left R module like this. So when I look at this submodule or left ideal generated by M, which looks like this, I can just multiply all of these things to the right by M. This will still give me a direct sum decomposition that looks like this. I haven't really done nothing. I just put M at the far right. Okay, but now I want to move the n closer to R. And that I can do because, for example, to move the m here, I just need to apply sigma to the minus I. In other words, I need to apply sigma inverse I times. So I get this. Okay, so this is what this submodule looks like. So the quotient, I can just do the quotient term by term. Okay, so in the degree 0 component, I have R modulo Rm. Well, Rm, this Rm is kind of stupid here. M is an an ideal, an R ideal. So Rm is just same thing as M. Okay. And in the other cases, I just have what? R modulo sigma to the minus I of M, which is what I called this field K sigma to the minus I of M. So this already gives me the description that I claimed in the proposition. Okay, and of course, I mean, each one of these summands is in a weight space. But if the orbit were not linear, there could be some collapses. For example, if sigma squared of m is equal to m, then, for example, here, when I have k is equal to 2, this space here, when k is equal to 2, would actually also be here in the weight space corresponding to m, because sigma squared of m is m. Okay, so things would be folding. You'd see some things identifying with itself. Since the orbit is linear, this is not the case. So this is already the decomposition of this universal module here as a sum of its distinct weight spaces. So it's kind of nice. Okay, so now why does this? I mean, it's not so common that objects have unique simple maximal submodules. So why is this the case here? Well, the case is that if I have a submodule, I know that the submodule is still a weight module. That's the exercise, right? So I can still, if I have a submodule here, I'm not assuming it's maximal yet, I have a submodule, I can decompose it as a sum of weight spaces, which are actually subspaces of the weight spaces of A, because N is a submodule of A. So for example, the weight space corresponding to this ideal here, sigma to the k of m, must be contained here because that's the corresponding weight space for am. Okay? But this is a field. I mean, these elements here are, elements of R which are invertible modulo this ideal. So there are only two possibilities for this space here. It's either 0 or it's this whole field. There's no middle ground. Okay, so this weight space is either 0 or it's everything. Well, let's recall that this module AM is actually generated by this element here, which corresponds to the class of 1 in the quotient. Okay, so clearly, if the weight space of n corresponding to m, which would be contained here, if this weight space were not equal to 0, then it would be equal to everything, R mod m, right? It would be equal to this field here. But this generates A of m. So n would be the whole of A of m because it would contain a generator of A of m, okay? So if this weight space is non-zero, then n would be the whole thing. So this tells me that any proper submodule will have nothing in this weight space. M will not be a weight. So this tells me that if I have, so I'm going to maybe be a little bit more go slowly with this argument, because I mean, if you've seen it once, you know it very well. If you haven't seen it, maybe not so much. So I can consider, I mean, one way, I mean, if you think that you have an object that has a unique maximal submodule, one way, I mean, then you know what it looks like, okay? It must be the submodule generated by all the proper submodules. Because if it has a unique maximal submodule, any proper submodule must be contained in it, okay? And so your candidate for the unique maximal submodule must contain all the proper submodules. So if there's a unique maximal submodule, it has to look like this. What usually goes wrong is that this object here will no longer be a proper submodule. It will be too big, it would be equal to the whole object. Okay, what works in our favor is that I can guarantee that this is still a proper submodule. And why can I guarantee this? Because I know that all of these proper submodules, because they're proper submodules, I proved that the weight space corresponding to M is equal to 0. Okay, so all of these have nothing in the component corresponding to M. So when I add them all up, I get something that has nothing in the weight space corresponding to M. So if it has nothing in the weight space corresponding to M, it has to be a proper submodule. And so clearly by this definition, the problem is this a proper submodule? I gave you the argument, it is a proper submodule by the above. And so if it is a proper submodule, it has to be the unique proper submodule by this very definition here. Okay, because this contains, by definition, any proper submodule. Okay, so this is the proof that this universal module A of M contains a unique proper submodule. And so if I'm looking for simple modules, okay, I just need to find this unique proper submodule. Okay, a word of warning. I mean, I'm dealing with orbits, with the orbit of M, and you can think, well, it doesn't matter which ideal you pick in this orbit. If you pick M or if you pick sigma of M, it shouldn't matter. Well, it can matter. Okay, so this quotient here associated to the ideal M may be different from the quotient here associated with the ideal sigma of M. So you do need to look into this. Okay. In a lot of cases, they are isomorphic, but in general, they're not. I am going to skip cyclic orbits. They're more complicated. They're more interesting as well, but they're a bit more complicated. They involve a nice object called the Veronese subalgebra. So I'll leave that for you to look at. And I will go back to I'll go back to linear orbits. Okay. And I will start with examples. Okay. Well, let's start with the abstract example of this module A of M in general. I'm just assuming that I'm in a linear orbit. Okay. So I know what it looks like as a space, right? As a set. Okay. I know how the action of R works because R is just acting here on these fields, which are quotients of R. Okay. So what is the action of X? Well, for example, let's do a less obvious example. How does X act on Vk, where K is negative? Well, if K is negative, then Vk will be y to the minus K. And y to minus k times 1, right? But 1 in this field here is really the class, and this is why I'm saying, I mean, all of these fields are isomorphic, but they're different, and we need to take the difference into account, because the 1 here, in a certain sense, is not the same thing as the 1 in the other field. Okay, so the 1 here is the class of 1 modulo the ideal sigma to the minus k of m, which is here. Okay, so how does X act on this element Vk, which looks like this? Well, X wants to go to the right, and it can by applying sigma inverse, because the things here are things which are in R. So X will go to the right by applying sigma inverse. So when it applies sigma inverse, it does nothing to 1, but it adds a sigma inverse to this part. So I get sigma to the minus k minus 1. Okay. And then here we have this, xy to the minus k, okay? But since k is -1 or smaller, I mean, there's at least one copy of y here. K is not equal to 0. So I can isolate one copy of y and leave the other copies of y here, but x times y is equal to a. Okay, so this y to the minus k minus 1 is really just the vk plus 1 in this definition here, but there's an a appearing. But this A, which is an element of R, I need to interpret it here in this field, which has changed. Before, I was working in the field associated to minus k, and now I'm working in the field associated with minus k minus 1. So, I mean, I'm using this notation to signal that. It's the element A, which is an element of R, but I need to look at it modulo sigma to the minus k minus 1 of m. And so I'm calling it A sub k plus 1. I'm using the kind of the symmetric, okay? Because of this convention that I put a k here and a minus k here. Okay, it's just a useful convention. Okay, so this element A will have different incarnations, no pun intended, will have different incarnations in these different fields. Okay, and this is really important. So I give you an example of what the action of X is. I mean, if the action of X on a VK where K is greater than or equal to 0 is easier because, I mean, it's X's with X's, so you just add 1 to the exponent and kind of change your field here. Okay, so this is the action of X. The action of Y you can compute similarly, and the sigma of A will appear because you'll have Y times X instead of X times Y appearing. Okay, and so you can schematically look at the module like this. This is a little bit more abstract than with SL2. Okay, so these points here are the V's. So this is V0, V1, V2, V3, V4. In red you have the action of x. In green, you have the action of y. And this is very abstract. In blue, you have the action of r. Okay, but R can have many elements. I mean, even in the case of SL2, the two generators of R are H and T. So there are two different things which I'll have to look at, okay? And so according to these calculations, X will just act as multiplication by 1 and bumping in to the right. So X will always be moving to the right, Y will always be moving to the left, okay? From the vector V0 on, X will just be multiplying things by 1, but to the left of V0, X will be multiplying by A, interpreted in all of these different fields, okay? Very good. Let me just change something here, which is not... This is why, I mean, so I was looking at this, which I only finished preparing these slides a couple of minutes before the lecture, and there was some incongruence here, and I think it's because of this. I still call this A minus K minus 1. Okay. So this is, it's just notation, you can figure it out if it's not matching. So this is what the action looks like, okay? Now, okay, we look at this and, okay, how can I find the unique maximal submodule? Is this, I mean, it's possible that the unique maximal submodule is equal to 0 if this module is already simple. If it's simple, then the only maximal submodule is 0. So how do I look at this? Well, it really depends on whether or not these things here are equal to 0 or not. Okay, so if they're all non-zero, then it's easy to show that this module is simple. Okay, what does it mean for all of these things to be non-zero? So for example, what does it mean for this A0 not to be 0? It means that A modulo M is not 0. In other words, A is not an element of M. What does it mean for A minus 1 not to be 0? It means that A modulo sigma inverse, modulo sigma of M is not 0. In other words, A is not in sigma of M. Okay? This means that A is not in sigma squared of M. This means that A is not in sigma cubed of M. And you can do the same game here. So what really matters is, does one of these ideals contain the element A? Because if it does, one of these numbers appearing here is going to be equal to 0. So this leads to the definition of what's called a break. Okay, so a break is a maximal ideal which contains the element A. Okay, so let's consider the easiest case, which is there are no breaks. Doesn't sound good. We like to have breaks, but in this case, no breaks, it's easier. Okay, so assume there are no breaks. Okay, if there are no breaks, all of these numbers are non-zero, all of these numbers are non-zero, and I can actually convince you right away, if you did your homework, that this module needs to be simple. And why is that? Because if I have a non-zero element here in this module, I can look at it, I look at its components here. And if I have a submodule, then it will be a weight module. So it will contain some weight, some non-zero weight vector. For example, it will contain, for example, this one. But with this element, I can generate all of the other ones to the right by acting with X. And I can start generating the ones to the left by acting with Y. The only problem is, for example, if this number up here were equal to 0, because if this number were 0, from here, I could not reach here. But if this number here is not 0, I can get this one, and this one, and this one, and this one. So this module will be simple if there are no breaks. Okay, and moreover, this is not, well, it's not so important, but using the fact that these elements are non-zero, I could do a change of basis and make the module, I mean, it's kind of a little bit frustrating that I have numbers here and ones here and ones here. This doesn't seem very uniform. But in the case of no breaks, then I can do a change of basis, which looks a little bit, you can maybe do that as an exercise. That you can assume that X will always be acting as 1 and Y will always be acting like this. okay, if there are no breaks. So the module, looks very simple. Again, no pun intended. It is really simple. And we have learned something new. We have found a new irreducible module for SL2, which is infinite dimensional. And even for people who know about Verma modules, they haven't seen this one because this is not a Verma module. Okay, so remember that SL2, so let's now work out this example with a little bit of time. SL2 is a generalized Weyl algebra over this polynomial ring in two variables. Okay, this is how H acts. This is how sigma acts on H. This is how sigma acts on T. Okay, so you can do, I mean, from this you can see how sigma to the k acts on H, like this. This is the easy one. And how sigma to the k acts on T. This is easy as well, not so immediate. So first of all, what are the maximal ideals of R? Well, if the field is algebraically closed, the maximal ideals, no Stellensatz, for example, you can use that. The maximal ideals look like H minus lambda, T minus mu, where lambda and mu are scalars, are elements in your field. Okay, I'm assuming the field to be algebraically closed. Okay, so this is what all the maximal ideals look like for different values of lambda and mu. Okay, so when I act by sigma to the k, patient, you do a calculation, this is what the ideal looks like. Okay, so let's see what the elements, since I'm going to use this description here, assuming that there are no breaks, okay, I only care about the value of sigma v, the incarnation of sigma v in all of these fields, so modulo all of these sigma to the minus k of m. Okay, so I'll do the calculation here. Let's not waste too much time. Assume that I haven't messed up the calculation. So modulo sigma to the k of m, sigma v is just a scalar, because notice that all of these quotients are isomorphic to f, right? I'm getting rid of h and I'm getting rid of t. But in the appropriate place, the sigma v looks like this scalar here. So it depends on the k, because it, as I said, I mean, it has different names in all of these different fields, even though all the fields are isomorphic. And in this case, they're all isomorphic to f. Okay, so this is sigma a. So this is what the module looks like. Okay, here I've just, because this is what matters, I've just put down the action of h. I haven't put down the action of t because, I mean, I don't need to. If I know the action of x, if I know the action of y, because, I mean, of course now, f is x, e is y, and h is h. So now I've gone back to the generators of SL2. So this is what the module looks like. Okay, so when is this module simple? When there are no breaks. This means that all of these numbers are non-zero. So this module will be simple if and only if this is true. Okay, this mu is never of this form for no integer. And you can find tons of examples. For example, take lambda equal to 0 and mu not an integer, then this will always be true, right? Because if lambda is 0, k plus 1 times k is an integer. So mu is not an integer, mu will not be of this form. But there are many, I mean, there are many solutions to this, okay? And here I'm just giving you infinitely many, okay? So I will get a simple module for SL2, which is infinite dimensional, and it does not look like a Verma module, if you know what a Verma module is. E is not acting locally nilpotently. Okay, so it's, well, we've already gained something by this abstraction. Okay, very good. Well, what happens if there is one break? Let's allow ourselves one break. It's not too bad, not be too strict. Okay, so let's assume, just for simplicity, that I'm calling that break M, and so I'm doing the construction A of M for the break M. Okay, then this looks the same, but if A is in M, so if M is a break, that means that A, which was appearing here, interpreted in this field here, has value 0. And if this is the case, I don't know what the other values are, okay? But just knowing that this thing here is 0 tells me that the span of all of this here, including the -1 and everything to its left, will be a submodule. Why is that a submodule? Well, why is it stable under the action of x and y? It's clearly stable under the action of y because y is just moving to the left. It's also stable under the action of r because r is kind of staying within each space. The problem is moving to the right. So when I cut it off here, I would have a problem if I were able to go from here to here. But since this is a 0, I'm not able to go from here to here. So this is certainly a submodule. Okay? I don't know if it's the maximal submodule or not because I don't know what the value of these things are. Okay, so let's not jump to conclusions. I mean, if there's only one break, this is it, and then this will be, this will be the maximal submodule, but I don't need to assume that yet. So this will certainly be a submodule, and so I can certainly consider the quotient of this by the submodule. Okay, and this in a generalized Weyl algebra is what looks like a Verma module. And in the case of SL2, which is this example, so if I want the ideal M to be a break, I need M to contain the element T. So I'm taking M to be of this form. Okay. The calculations are already done. Now they're easier because mu is equal to 0. So just go back and see what happens. Now I cannot do that change of basis of putting everything below as 1s and everything above as sigma of a's. So I need not only to see what the value of sigma of a is, I also need to see what the value of a is and what the value of h is in the quotient. Okay. And the module looks like this. When I quotient by the submodules, this is already taking the quotient by everything that was to the left. Okay, so in the quotient, this element here is going to the quotient submodule. So now in the quotient, it's going to 0. So this is looking more like what we're used to in SL2 in this case. Okay, so here the element E will be sending this to 0. And the element F is just kind of constructing all of the module from this vector on, okay? And the element E is acting with these eigenvalues, okay? This will certainly always be a module. Might not be simple, depending on whether or not I have breaks, but this will always be a module, and it's in fact called the Verma module, associated to the scalar lambda. Okay, so we've already constructed the Verma module for SL2, but more importantly, we've constructed some that we hadn't seen before, which were kind of doubly infinite in both directions, simple module for SL2. Okay, so when is this module simple? Well, it just depends on whether any one of these numbers here is equal to 0 or not. Okay, how can this number be 0? Well, one of these numbers be 0? Well, lambda would have to be 0 or 1 or 2 or 3 or 4. So lambda would have to be a non-negative integer. So this module is simple if and only if lambda is not a non-negative integer. And this is the result that's known for Verma modules for SL2. Okay, so when lambda is not a non-negative integer, I will always have a simple module, and this means that this is the unique break. The ideal that I started it with is the unique break. There's only one break. Okay, what happens if lambda is a non-negative integer? Then one of these things up above here is going to be 0. And let me just show you by example. Imagine, well, let's imagine, so I use the same example. Imagine that this number here is equal to 0. Okay, I'm going to ruin my drawing. Imagine that lambda is equal to 4, so this number is equal to 0. Okay, I have all these dots. Then my claim is that all of this here will also be a submodule. And this is because, well, there's no problem with the action of the red one, which I think I forget. I think the red one was Y probably, or X. I don't remember. There's no problem with the action of this red generator. Okay, the problem would be with the green. Okay, but there's no problem because when I try to go from here outside of what I'm saying is a submodule, this is 0, so I don't really go outside. So this will be a submodule, and now this will be clearly a maximal submodule because none of these other scalars are equal to 0. Okay, so for example, when lambda is a non-negative integer, here's the example of L4. I have this submodule here, so in the quotient, if I also quotient out by this, I have this finite string, and this is the module we've seen before, and we called it L4. Okay, so we've recovered everything. We recovered the finite dimensional simple ones, we've constructed the Verma modules, and we've even constructed an infinite, a doubly infinite simple module, which some of you might not have seen before. Okay, so this is quite nice. Okay, let me just give you a final example, which again, well, this is well known, but maybe you haven't seen it before. What happens, for example, if mu is equal to minus lambda? Okay, well, here are the calculations. I'll spare you that. It looks like this. Okay, there will be a 0 here. So if there's a 0 here, I know that this will be a submodule. So when I look at the quotient, I am just forgetting about all of this. So let's see. I'm going to erase this. Okay, when I look in the quotient, the module looks like this. Okay, and it might be simple or it might be not simple. So in the quotient, this here will be acting as 0. Okay, it might be simple or it might not be simple. It will really depend on the value of these numbers here, whether or not they're 0. Okay, but it will certainly be a module. It will certainly be a representation. Okay, and it looks very much like the Verma module, but it's going in the opposite direction. So this is what's called a dual Verma module. We've switched the roles of E and F, and we have a Verma module, but going in the other direction. So in Verma modules, we call them, they're examples, they're universal highest weight modules, because, there's a unique highest weight, which is lambda, but here lambda is not the highest weight, it's exactly the opposite. It's the lowest weight, it's the smallest integer here. This is lambda plus 2, lambda plus 4, so this is the lowest weight module. Okay, so you get a dual Fermat module. So all of this comes in the theory. Okay, and you can experiment with other things. Okay, okay, this is my last slide. This is yeah, my playground where I was trying to get these diagrams. So I mean, you can see that for SL2, this gives you really a lot. So you can imagine that gives you a lot of stuff for a lot of algebras, and we've only explored, even for SL2, we haven't explored all of it. You can consider, you can get some indecomposable modules using these. And then, of course, if you're interested in modular representation theory, so representation theory in prime characteristic, then typically this will be the case when you will get cyclic orbits. Cyclic orbits are a little bit more complicated because as I said, things will collapse, several of these weight spaces will be added on, and so it's kind of like you have a circular thing, but you can still, you can get them with the theory with circular orbits, which I didn't really explain, but the idea is that if you have an orbit with 3 elements, you have these 3 weight spaces, which can be kind of big, and you need to know the arrow that was going to the right. Now, of course, the right is actually this one. Okay, so you're going around in one direction and you're going around in the other direction, and you need to know how to do this. One way, if you're interested in simple modules, is when you go around, you multiply by a scalar. Okay, and you'll get different behaviors if that scalar is 0 or if that scalar is non-zero. Okay, and this will give you essentially the simple modules in the modular case. Okay. If you want indecomposable ones, then the trick you can do is you look at one of the, for example, the terminal weight space, and you get some. If you want an indecomposable which is not simple, you get something which is bigger than the field. For example, 3 copies of the field, and there you introduce an endomorphism of that field, K3. say, so like an endomorphism of a three-dimensional vector space, which can be represented as a Jordan block. This will guarantee that you'll end up with an indecomposable module. Okay, I mean, you need to fix then the action of the other generators so it all matches up. This is possible to do, and you'll get indecomposable modules by doing this. So, I mean, even if you're not just interested in simple modules, at least the idea of this weight theory can be very helpful to, you know, to generate other ideas, to compute a lot of examples. So I will finish here.